Hi, mathematicians. I thought we might make some lunch here. This little hedgehog wants to make some lunch. He's going to make some lunch for the alligators and the tigers to join in. We're going to have a big picnic outside, and we thought we'd have some sauteed snake for lunch. We'll go ahead and set this aside and let it keep cooking while we talk about lesson 3.2. So lesson 3.2 is using the longest factor strings that you found in lesson 3.1 and applying them to problems. So there's all kinds of information on this page that I'm going to talk to you about, but your actual work then starts over here on this. So I'll come back to this in just a moment. So these are some pieces of information you may already know, but I want to go ahead and make sure that everyone's on the same page and we all have this information while our food cooks. Okay, so we're going to be working with exponents a lot. Exponents are the small little numbers written in superscript to the right of a regular size number. The regular size number is called a base, and the smaller number is called an exponent. So this particular example is 5 3 times. So this tells you what number, and this tells you how many. So it's 5 times 5, which is 25, times 5, which is 125. So this number equals 125, which is what this equals when you multiply. Okay, you can also see these things written as a set of 2 bases with their exponents. So 2 to the 3rd power times 5 to the 4th power looks like this. 1, 2, 3, and then 1, 2, 3, 4. And when you multiply all of that out, because notice there's a multiplication sign in between, you get 5,000. Okay, if you take away one of the exponents, so instead of a 2 to the 3rd power, it's a 2 to the 2nd power, and you only write the 2 twice, but you still write all of the 5s exactly as it was before, you're going to end up with a smaller that is one multiple of 2 smaller than it was before. So our answer was 5,000, but now we have to divide that by 2 to get our new answer. So this answer is 2,500. If we added that 2 back in, we'd take this number times 2 and we would end up with 5,000. So in that same thought process, you can also take where this was 2 to the 3rd power, now we're going to make it 2 to the 4th power. So we take this answer, 5,000, and you multiply it by 2 because you'll have one extra 2. It'll be 4 2s. It'll look like this. 3, 4 of them, and then all 4 of your 5s. 1, 2, 3, 4, 5s. It'll be this answer times one extra 2, which will be 10,000 instead of 5,000 because it's that number times 2. Okay, so those are some basic pieces of information that you'll be using for problem 3.2, but the primary thing you're going to be doing is prime factorization, which we talked a little bit about in a previous Khan Academy video, and you did slightly on 3.1, but we're going to be practicing a lot more today. So here's an example of what you will be doing today. So let's say I have the number 48. So I need to write it like this, and then I need to come up with a multiplication problem that equals 48. There's all kinds of numbers I can use. I'm going to go ahead and do 4 times 12. Okay, those are a set of multiplication facts that equals 48. Neither of these numbers are prime, and we want to keep working until we get all prime numbers. So I'm going to take this level down one more branch. I have to think of a multiplication problem that equals 4 that is not 1 times 4, because 1 times 4 won't get our branch anywhere. The only possibility is 2 times 2. These are prime numbers, so this branch is done and this branch is done. So this whole side is now finished. This side over here, 2 times 2 times 12 equals 48. And 4 times 12 equals 48. So those are different ways of thinking about numbers that you can make to equal 48. We need to continue with this side. So I need a multiplication problem that equals 12 besides 1 times 12. I can either do 2 times 6 or I can do 3 times 4. It doesn't matter. I'll choose 3 times 4. I went ahead and circled my 3 because 3 is prime. However, we know 4 is not prime because we already encountered that before. Now I'm going to do 2 times 2 equals 4, so I can make each of these branches also end in a prime number. So I've circled every branch as it's ended, so I know exactly what numbers I need to multiply to equal 48. 2 times 2 is 4, 4 times 3 is 12, 12 times 2 is 24, 24 times 2 is 48. So we have 1, 2, 3, 4 twos. 1, 2, 3, 4 twos, written first because the 2's are smaller than the 3. We also have 1, 3 circled, so we write 1, 3. This is the answer that equals 48. These are all prime numbers. This is the prime factorization of 48. This is an acceptable way to write it, but the best way to write it is with exponents and a base. So my base is 2, my exponent is 4 because I have 1, 2, 3, 4 2's, and then those are, a 2 is smaller than a 3, so I wrote it first, and a 3 comes last. Okay, I want to demonstrate very quickly for you that it doesn't matter how you start your problem, you will still get 48. So let's say that I had started this problem a different way. Let's say that instead of 4 times 12, I did 24 times 2. And 24 times 2 is right here. 2 times 2 is 4. Actually, I'm sorry, I lost my train of thought. But anyway, we're going to do 24 times 2. So 2 is prime, so I'm going to go ahead and circle that branch. But my 24 is not prime. So 2 times 24 equals 48. We need to continue with this branch right here. So to equal 24, I'm going to do 12 times 2. So there's another 2 that's prime, and here's a 12 that's not prime. I need to continue on with my 12 branch. I'm going to do 2 times 6 instead of 3 times 4 as I did up here. 2 is prime, so I circled it. 6 is not prime, so I need to keep going. And I'm going to do 2 times 3 to equal 6. 3 is also prime, so I'm going to circle it. Now I have 1, 2, 3, 4 2's, so it's 2 to the 4th power times I have 1, 3. So I end up with exactly the same answer I had before. Okay, let's do this one more time. Let's use 90 this time. Okay, I need any multiplication problem that equals 90. The easiest one probably is 9 times 10, neither of which is prime, so both branches must continue. 3 times 3 equals 9 is the only problem that equals 9 besides 1 times 9, and they are both prime numbers, so I'm going to circle them. You circle them once they become prime. 10, I only have 1 times 10 and 2 times 5, so my only choice is 2 times 5. So I'm going to circle each of these because they are prime. So the prime factorization of 90 is 2 times 3 to the 2nd power times 5. So I wrote the first number that was the smallest, then I wrote the next smallest number as a set of exponents. So if it asks you to write it as exponents, this is how you're writing it. This is a factor string, these are exponents in exponential notation. And 5 was last because it was the largest of them. Okay, this is what you're going to do in this problem. So let me walk you through what it's asking you to do. We are skipping a few parts, so make sure that you follow these directions so you don't have extra work. The first thing it asks you to do is find the prime factorization of 36. So after I set up my page with the 3.2 at the top, name, date, A1, we're doing A1. You want to do prime factorization of 36. So you're going to do this branching upside down tree thing, prime factorization, but of 36 instead of 90. So I left myself plenty of space here to do it, and you can take more space if you need it. So we are doing A1, and then we are skipping all the way down to A5. A5 wants you to use a multiple of 36. You may do 36 times 2, 36 times 3, 36 times 5, 10, 36 times anything. You're going to write that number right where I've written this blank, right where the 36 is above the upside down V. Then you're going to do prime factorization, this process, for that multiple of 36. What you should notice is that these are pretty similar. And for question 5, it asks you to explain how they are the same. So I wrote, these are the same except, and tell what's different about them or what was added or something. Okay, B. B wants you to find the prime factorization of 10, 100, 1,000, and 10,000. So for B, 1A, I've written 10, 100, 1,000, and 10,000, and then left myself space to work the problems in this manner. Doing the same thing again. Okay, for B2, it has a little bit of an explanation of you how these numbers can be written as a power of 10, and it has an example of 10 being the base and the exponent being either a 1, 2, 3, or 4. So the exponent changes depending on the number of zeros. So we have 1 0, so we have a 1. We have 2 zeros in 100, so we have a 2. And we have 4 zeros in 10,000, so we have a 4. And so then it wants you to take that idea and apply it to how many zeros there are here with the 27 in front. So B2, after you find the prime factorization of these, you want some number times 10 to a power to equal 270. So it's going to look something like this, 10 to the third power, or 10 to the fourth power, 10 to the something power, times, you need to get that 27 in there somewhere. So think about how you're going to do that. Okay, moving on to C. In this case, they have done all of the work to get this answer. They want to know what number you started with. So they give you 2 to the fourth power times 3 to the second power times 5, and they want you to tell what the number is equal to. So you'll have to do some multiplication to get that answer. For C2, it wants to know if inside of this whole set, 2 to the fourth, 3 to the second, and 5, if you see 2 to the second times 3, or 2 times 2 times 3, as part of or a factor of what you did in C1. So I wrote yes or no, this is or is not a factor of this part up here because it asks you to explain it. Explain. Okay, for C3, this person claims that adding an extra 2, so it was 2 to the fourth power, now it's 2 to the fifth power, adding an extra 2 there makes this a multiple of C1. So is this a multiple of this? Think back to the example I did at the beginning of your video. So I wrote that out like this. It is or is not a multiple and explained. Okay, for part D, you need to calculate which of these answers down here are equivalent to each other. Try to do it without actually doing all of the math, but just using mathematical reasoning. So you might have to write all 4 of these. You might choose 3 or 2 or 1, or you might even say that none of them are equivalent. And E, the very last one, I had to add on the back of my paper. If you do that, make sure that you make notes to yourself, that you know that you've been continuing on to another page. E says, how many unique prime factorizations of a number are there? I wrote there are blank unique prime factorizations for each number. This goes back to the problems that we did in 3.1. Hopefully you remember that. And you figured out some in this problem as well. Okay, you are going to complete 3.2. You're going to work on that in your math notebook. You're going to snap a photo of it and upload it as your assignment. Let me know what questions you have about it. And let's see how our sauteed snake is doing. It looks like it's about ready. I hope you guys can come over for dinner.